All right, thanks for coming out to my parents' garage this afternoon. I'm going to be talking about the NP hardness of automating the cutting planes proof system. This is joint work with Sajin Karoth at SFU, Mika Goose at Stanford, and Tony Patazzi, my advisor at University of Toronto. All right, so let's quickly talk about cutting planes in its original context. So cutting planes was introduced by Gomery in the 50s as a way of doing integer linear programming. So the setup here is that you have a polytope defined by some linear inequalities A, and what we care about is optimizing over the points in the interior of the polytope that have integer coefficients. So we don't care about all the fractional points that may lie on the boundary, on the edge, which is where optimization tools will usually take us. And so what we want is a way of constraining the polytope so that the inequalities on the boundary are closer to the integer convex hull, or rather the convex hull of the integer points on the interior. So Gomery introduced a number of rules for doing this, for introducing new linear inequalities, and it saw a revival in the late 70s and early 80s when Schottel showed that actually these rules were practical to implement. And so this was a good way of doing integer linear programming. So for us, the story's going to start a little bit later. We're going to move to the late 80s, where Cook et al. Introduced cutting planes as a system of refutation. So now, as compared with the previous setup where we were looking for the integer points in the interior of the polytope, now there are no integer points in the interior of the polytope, and what we want to do is certify that fact. So here again, we want to introduce new linear inequalities that further constrain the space and down until we get to some kind of contradictory line. More formally, our setup is going to be that our input is some set A, which we call the axioms. We're going to derive from the axioms new linear inequalities. And at the end, what we want to prove is a contradictory line, 0 greater than or equal to 1. And this will be considered a refutation of A. So how do we derive these lines? I'm not going to go into too much detail because originally it was introduced, cutting planes was introduced with a series of rules for how to do these derivations. And this is the so-called syntactic cutting plane system. But what we're happy to deal with is semantic cutting plane system, where if you have two linear inequalities, you can derive any new one as long as any integer valued point that satisfied both of the original lines satisfies the new one. So here we can see that this orange line is a sound derivation from the two purple ones because all four of these integer points on the left-hand side satisfy the orange one as well. And notice from this derivation, we've cut out this huge piece of the original polytope, this piece shaded in orange. And so continuously doing this, we can get down to an empty polytope and from there to a contradictory line. Okay, so we're going to be talking about the algorithmic problem, which is how efficiently can we actually do this procedure? How efficiently can we get to a contradiction? Obviously, this is a useful thing to care about because originally this came from linear optimization, and there what we really care about is algorithmically finding the integral points. And so here, again, we're going to care about the efficiency of refutation. So normally this would be measured in terms of the input size. Say we'd want an algorithm running in time polynomial in the number of axioms. But we're going to shift the goalposts a little bit and talk about algorithms running in time polynomial in the size of the shortest refutation of A. And the reason for this is just that sometimes there are no poly-size refutations in cutting planes. Some axioms sets require actually an exponential size cutting planes proof. And here it would be kind of ridiculous to assume that our algorithm should be able to give us something in polynomial time, in the length of the input at least. But we can ask for it to not take too much longer than it would have to if it could find the shortest proof. And what we prove is a lower bound that shows that actually doing so is NP hard. So there are, assuming P doesn't equal NP, there are no algorithms that in time poly of S can actually find cutting planes refutations in general. And since this problem is in NP, this is basically a tight result. Okay, so this is part of a general framework called automatability. So to talk about automatability, let's talk about proof systems in general. A proof system P is just a way of deriving a contradiction from a set of unsatisfiable axioms via sound deductions. So in our case, this was getting any linear inequality that maintained all the integer value points. And then the automatability question is, can we find P refutations in polynomial time? So let's look at another system, and in particular a system that people really care about in proof complexity and in algorithms. So this is resolution. In resolution, the input axioms are clauses. So you can think of the input as an unsatisfiable CNF. And what we're going to derive for a contradiction is the empty set, which you can think of as a clause that's trivially unsatisfiable. And our deduction rule, our sound deduction, will be the resolution rule. So given two clauses, which have the same variable occurring in different directions, positively in one, negatively in the other, you should be able, or you can derive the OR of those two clauses with that variable removed. And it's easy to check that this is a sound deduction. So again, this is a very practical system. It shows up in SAT solvers, automating first order logic, and a number of other places. So we do really care about automatability for resolution. And in a certain sense, res is automatable. In particular, it's width automatable. So the width of a resolution proof is just the maximum number of variables occurring in any line in the proof. A line, recall, is just a clause. And what this theorem says is that if there's some resolution refutation of tau, which has width w, then we can find a resolution refutation in time n to the w. Again, not necessarily that one, but we can do that. And this is pretty good. And it turns out this is actually known for most of the systems that we study, except for very strong systems like Frege and IPS. So in particular for Knowles-Delinsatz, polynomial calculus, Shirali-Adams, and sum of squares, there's a degree automatability algorithm where, again, degree automatability is just the arithmetic version of width automatability. So if there's a proof of degree d, then you can find it in time n to the d. But it should be noted here that cutting planes is an outlier in that it's very much not degree automatable. And this is just for a very simple reason, which is that cutting planes has degree 1 in every line. It's linear inequalities. And so degree automatability would be asking us to be finding cutting planes proofs in polynomial time. And as I stated before, a lot of times there isn't even a polynomial size proof. So this brings up another question, which is how good are these width and degree automatability results? So first of all, they're tight with respect to width and degree, but it's worth noting that the width can be as big as linear in n. Remember, it's the number of variables occurring in some line, and maybe all of the variables show up in some line of the proof. So in those cases, all we're getting is an exponential upper bound, which isn't very helpful. A priori, it's not very helpful. And in general, talking about n and the width, it'd be nice if we got upper or lower bounds just in terms of this parameter s that I told you is kind of the right notion for automatability. And in 2001, Algorithmic and Razvarov showed that actually resolution isn't automatable, assuming the exponential time hypothesis. So this was this was the first result of its kind for resolution. It was a pretty major result, and it stood as the benchmark for a very long time. And it was only last year where, kind of out of nowhere, Atsarius and Mueller proved that the same problem is actually NP hard. And again, since this is actually a problem in NP, you can check whether a given resolution refutation is valid. This completely closes off the problem. Okay, we're not going to go into their reduction too much. The key piece that we need is their lemma, where they show how to turn 3 SAT instances into unsatisfiable CNFs such that the size of the smallest cutting planes refutation depends on whether the 3 SAT instance was actually satisfiable or not. So this is the usual notion of a reduction, even though it's a little bit counterintuitive because you're turning something that could be satisfiable into something that's definitely unsatisfiable. But what they show is that if f is satisfiable, then the transformed formula tau sub f has polynomial size resolution refutations. And meanwhile, if f was unsatisfiable, then the smallest resolution refutation has at least exponential size. And just to see why this gives their main result, if you assume that there is some automatability algorithm, AUT, which runs in time poly s, then we can first transform f into tau f, and then run AUT on the resulting formula. Now, in the case where f is satisfiable, since there's a poly-size refutation of tau, and AUT runs in polynomial time, it will take, after a polynomial number of steps, AUT will halt and return either the proof or even just say, yes, there exists a proof. That's enough for us. Whereas on the flip side, if f was unsatisfiable, then there's no way that AUT will halt in time, considering the smallest resolution refutations of tau are of exponential size. So this is good, and this points us to our main lemma to prove our main theorem, which is an equivalent transformation for cutting planes, transforming 3 SAT instances into unsatisfiable systems of linear inequalities. And in fact, we are going to piggyback directly off of Itsarius and Mueller's result by transforming their unsatisfiable CNF into a system of linear inequalities instead of working directly from 3 SAT. So this is a more general process called lifting, and it's going to be the topic of the rest of our talk. All right, before we go on, any questions? All right, good. So before I get into the nitty-gritty of lifting, let's ask if the question is trivial, and also how we transform CNFs to systems of linear inequalities in general. So there's a direct transformation, which is very simple. If you want to assert that one of the variables in your clause is true, you can instead add them up as integers and then ask if the result is at least 1. And here, of course, you want variables to be mapped to themselves and negated variables to be mapped to 1 minus themselves. And then, of course, we enforce the condition that every variable is between 0 and 1. And so when we look at the integral solutions to this, we get exactly the Boolean solutions to tau. So we could ask if this is just enough, if we can do this generic transformation and have our cutting planes result, but life's not that simple. So cutting planes is a stronger system than resolution in the sense that if you do this generic transformation from tau to A, the cutting plane, the size of the smallest cutting plane's refutation will be at most polynomially bigger than the size of the smallest resolution refutation of the original tau. But the other direction doesn't hold. It could be that the cutting plane's refutations of A have exponentially smaller size than the best resolution refutations of tau. And we have examples where this is true. So I'm going to oversimplify things a little bit and say that the reason that cutting planes can be stronger than resolution is how they relate to the variables. So in resolution, you're interacting with one variable at a time, cutting on a variable which occurs positively in one clause and negatively in another. Whereas for cutting planes, all your linear inequalities are expressing some kind of rich relationship between all of the variables simultaneously. And our derivations, again, we're allowing semantic derivations, although even for syntactic derivations following the rules, these derivations can really can make big jumps in terms of the relations between the variables. And so what our strategy is going to be is abstracting away from the original variables. We're going to somehow make it so that whenever cutting planes wants to deal with, say, x1, it has to do so much work that pretty much all it can do is do something like the resolution rule. basically express very simple logic only on the original input variables. And this brings us to gadget lifting, which is the idea where we replace each original variable xi with a function on some fresh set of variables. So this inner function is called the gadget g, and the idea is that now a will never have direct access to the xi variables, and if we choose g well enough, a can only ever really do simple things with the original variables because it has to reason about g in the interim. And from this, we can hopefully take resolution lower bounds and bring them to cutting planes lower bounds. So our dream would be a theorem like the one at the bottom, which says that when you compose tau with this gadget g, the shortest cutting planes refutations of the composed tautology are about the same size as the best resolution refutations of the original tautology tau. And we're going to need a fudge factor in here, which is like the complexity of computing the function g itself using linear inequalities. So this is nice, and this would be great. It turns out the right notion is a little bit different, and this is a result due to Garg, Goose, Kamath, and Sokolov from a couple of years ago, which says that the log of cutting plane size of the composed formula is equal to the width in resolution of the original formula. Again, times this fudge factor of log n. I don't have great intuition to impart about the log on the left-hand side. It has to do with this thing called balancing. But on the right-hand side, this width, recall, is like a measure of how many variables you have to deal with at any one time in the resolution proof. And so for each of those variables, since we're doing like log n work to actually read it, this is like the amount of work that cutting planes has to do to actually deal with one clause or in a resolution proof. So it's something along those lines. For our purposes, what we really want to know is this enough? Are we done once we have this theorem? So let's quickly check it. At the top, I just rewrote it in a form that'll be more useful to us. And now composing the Itzerius-Mueller transformation from F to tau and the GGKS lift from tau to A, we get that the size in the satisfiable and unsatisfiable cases is n to the width, the resolution width in their respective cases. So if we have a good gap in the width, then we're done. But I haven't given you anything about a gap in the width. And Itzerius and Mueller ultimately prove a gap in the size, the resolution size. So what we want is for, again, the width of their formula to be constant in the satisfiable case and polynomial in the unsatisfiable case. Then we get our theorem. Well, unfortunately, this isn't true. Turns out the resolution width of the formula tau is linear, no matter whether F was satisfiable or unsatisfiable. And so now we've fixed the lower bound in the unsatisfiable case, but we've completely torpedoed the upper bound in the satisfiable case. Thankfully, they do prove that a related notion of width, called block width, has this separation that we want. And block width is a pretty standard thing used in proof complexity, so we're going to go over it, and it's going to lead us into our main result. So recall that the width of a line is just the number of variables in it. And the intuition behind block width is going to be that we're not going to measure how many variables there are, but how well behaved they are. So first of all, I have to define some blocks, and I'm not going to tell you how I got these, but I'm just going to give you these this chunking up of the variables into B1 through B4. And now the block width asks, how many blocks does this line actually touch? And so you can see it touches B1 and B3, so the block width is 2. And of course, if I had taken a different chunking of the variables, like made each variable its own block, or had one block with all the variables, the block width could vary all over the place and become completely useless. So why we care about block width is that we want to pick our blocks very carefully so that we can separate good and bad instances. Here I've given you two lines, both of which have width 5, so the same number of variables in them. But line 1 has a lot of variables in a very few number of blocks. And on the flip side, N2 or L2 has very few variables in each block, but it does touch all of the blocks. And so we get this disparity in the block width. And what Atzerius and Mueller show is that for a very natural blocking up of the variables, in the satisfiable case, there is a resolution refutation which only touches a constant number of blocks in each line in the proof. Whereas in the unsatisfiable case, every resolution refutation of tau touches a polynomial number of the blocks at some line in some clause. And this is a kind of theorem that gets shown all over the place. For example, you could think about the pigeonhole principle in proof complexity. There's a natural blocking up there as being like the number of each pigeon or each hole. And this is a standard way to get lower bounds. And then the next step is also pretty standard once you have width or block width, which is a theorem that relates the resolution size to the block width. And this isn't a generic transformation. This requires a well-behaved formula that, roughly speaking, behaves well under random restrictions. But none of this is important. What matters to us is that this is almost exactly like the GGKS result, but with resolution size on the left-hand side. If we had cutting plane size of the lifted tautology on the left-hand side, then we'd be done. And so that's what we prove. We prove a new lifting theorem which lifts the block width of tau in resolution to cutting plane size of the lifted formula. And here, once we compose with Atzerius-Mueller, just to check the numbers, we've got polynomial in the good case, exponential in the bad. And so this gives us our non-automatability result. So I'm going to say one or two words about where this lifting theorem comes from, and then I'm going to wrap up. So the main idea is that we want to charge the cutting plane's refutation for each block that it reads now, instead of each variable that it reads. And so the natural idea would be to have G output an entire block of variables instead of a single variable. So now, if your refutation only reads one block, then even if it's using all of the variables in that block, you only have to compute G once, and it will give you all of the bits that you care about. Whereas, if your block width is high, even if you have very few coordinates in each block that you care about, we're going to make you compute the entirety of G in order to get at those few variables. And so now, since you have to compute G for many, many blocks, you can get the lower bound. And so how do we guarantee that cutting planes can't partially compute this function G to get the variables it cares about? It turns out the right thing to go through is what's called multi-party communication complexity. So I'm not going to go into communication complexity, but people who have seen lifting theorems before know that these actually come not from proof complexity, but from communication complexity and proving lower bounds there. And when it comes to multi-output functions, where you want to say that computing few bits is the same as computing many bits, a multi-party communication turns out to be the right way to go. All right, so I'm just going to wrap up quickly with some open problems. In the wake of Atzerius-Mueller's result, there's been a number of proof systems shown to be non-automatable, assuming P not equal to NP. But there's a number of stronger systems for which it's only known under crypto assumptions, essentially because it's hard to prove lower bounds in general there. And some weak systems, which for other technical reasons, we only know hardness under, say, exponential time hypothesis. The real interesting one, I think, is sum of squares. Sum of squares is a very natural proof system, a very well-studied proof system, and a proof system that people care about algorithmically. But we know absolutely no lower bounds on automatability for SOS, not under any conditions. So this seems like the natural next step. And other than that, it would be nice to get more applications of the lifting theorems we prove in our paper. So we actually proved 2 lifting theorems because we got an auxiliary result for tree-like cutting planes. And here they are stated in terms of communication complexity or real communication. And it would be nice to see more applications other than the ones that we proved these theorems for, because these are kind of tailor-made for those, but they are more general than a lot of the known lifting theorems. And so it would be cool to see more done with them. All right, great. Thank you so much.